the Kinetic Energy Change Theorem, article 1011 of the book Mechanical Systems Calculations of the Marine Facilities. A little bit about the theory, the Kinetic Energy Change Theorem. What is the definition of the theorem? The difference in the values of the kinetic energy of mechanical system or energy received by the system over the certain period. For this is in the brackets, we can this indication of differences of the kinetic energies correspond to some of the work of the forces acting on the elements of the system. This is the work, mechanical work of the external forces, and this is total of the work of the internal forces. The kinetic energy change theorem of mechanical system can be defined as the equality change in the kinetic energy of mechanical system and total work of external forces acting on element of the system. Yes, this is in the case if we do not consider the internal forces as it is characteristics for the rigid body. For the elastic body, we have to account as well the action of the internal forces. If the mechanical system was motionless at the initial moment, then the T0 equal to 0, then we have only T. So the kinetic energy will be equal to the work of the external forces as it is for the rigid body. Let's consider the exercise. We have the mechanical system consisting of the definite elements indicated on the figure 10, 11, 1. The first element is a so-called weightless load. So we have the force applied here, but it's external force assigned here. The force depends on the location S. Location S of this, the first one load on the inclined surface, inclined for 30 degrees. This force F equals 50 multiplied in the brackets 3 plus 4 multiplied by the S. The second is the stepped Pauli. Oh, excuse me, no. The second is another one load on the other side. This weighted load in the mass of this load is 6 kilos. This 6 kilos mass, and it moves with the dry friction on the surface inclined for 45% mass, so is equal 6 kilos. We have the roller moved by the three between the fourth and the fifth stepped pulleys. This is the roller of the homogeneous distribution of the material. The mass of roller number 3 equal to 2 kilos, and the stepped pulleys we have 4 and 5. The mass of stepped pulley number 4 is 3 kilos, and the mass of this mass is distributed evenly by the rim or by the other rim of this definite one pulley. And the pulley number 5. The pulley number 5 of the mass 0, this is weightless pulley, as well the stepped pulley with 2 radiuses of the treats bending for the first on the like they consist of drum maybe of the bended treat connected with this load 2, and for the other rim we have the bended another one treat, weightless treat connected with the roller 3 and connected with the pulley 4, stepped pulley 4. Stepped pulley 4 possesses the mass, and the mass 3 kilos. This mass is distributed evenly by the rim of this fourth pulley. Pulleys number 4, number 5 has the fixed axis. So these two pulleys rotates around the fixed axis of the stepped pulley 4 and the stepped pulley 5. And this roller moves along the surface, horizontal surface. The coefficient of friction of loads first and the second of support equal 0.1, but it's not much important for the maybe the load first, because load first is the weightless, and we know for sure that the friction force rises only if we have the normal reaction to the surface at the direction of the wedge for the second load. But for the first load, we have just assigned the longitudinal forces which acts along the inclined surface for 30 degrees with not normal component to the surface. Okay, pulley 5 subject to constant moment of the resistance. Okay, pulley 5 so experiences this pulley 5 experiences resistance. The directions of resistance is contrary to the direction of the rotation of this pulley, and the load 2 experiences resistance as well directed the opposite to the direction of the motion. The direction of the motion we too have is we have the force applied here, and by the system of threads, it moves all elements mechanical system. Okay, and the exercise assigns to determine the velocity of the second load. At the moment when the first load moves at a distance for 1.2 meters. So when this load will move for 1 and 2 meters, then we have to find the velocity, what will be the velocity after movement of the element motion. Considering the motion of all elements mechanical system, what will be the velocity of the second load, considering the resistance force, considering the projection of the wage force onto the direction of the opposite to the velocity, the forces of inertia when we rotate this pulley, this roller. No, this is not pulley, because the reason of the moments, just only the moment of resistance we have here. So, and what could be the main methodological approach, and what is prerequisites methodological? The main methodological prerequisites could be the use of the kinetic energy change theorem. As we can see that the subject is about to find the velocity of the system under the action of the external forces moved. This work of the external forces which moves the whole system, and we have to find the velocity. So the idea is to use the momentum change theorem, maybe in the last one definition, because this system goes from the state of rest, so T0 equal to 0, and because the system consists of the rigid body and the unstretchable threads, then we consider the system as just a rigid system. Okay, so what to do first? Actually, we have to find the kinetic energy of the mechanical system, which in the more general approach consists of the kinetic energy of all 5 elements. Kinetic energy depends on the elements of the motion of the mechanical system. And to find the motion, the first idea is to redefine the elements of the motion of all elements of the mechanical system. This is the velocity of the motion, a translation of the load 1, the angular velocity of the stepped parallel force, the translational velocity, and this angular velocity of this roller when it moves along the horizontal surface, the angular velocity of this one stepped parallel, and this all redefine these all velocities by the velocity of the load 2 subject to find. We have to find load 2. Okay, so let's go from right to left. First, what is the angular velocity of the stepped parallel F? It is equal to the velocity of the load V2, because we have the unstretched thread here, so it moves with velocity F2 by the rotation of this pulley, and we have the internal radius of the pulley. Radiuses as well have to be assigned. Do I remember the assigned radiuses? Oh, yeah, radiuses was assigned. The radius of the force pulley, this radius is the two-stepped radius, the small radiuses, the lowercase letter R4 equal to 0.2 meter, radius external of the rim of this force pulley is 0.3 meter, radius R5 lowercase is 0.2 meter, and the uppercase letter R5 of the radius of the rim of this stepped pulley 5 is 0.4 meter. So what is the angular velocity of the stepped pulley 5? We have to divide the velocity of this point of the motion, of the condition of the thread to this load, the same as the velocity of the point on the older circle of the smaller circle rim of this fifth pulley, and this radius is R5. Okay, so the angular velocity of the pulley 5 is V2, V load 2 divided by the internal radius of this stepped pulley, R smaller case R5. So what is the velocity V3? We go gradually from right to left. v3 because it's the same velocity as the velocity translation of the point C. The velocity translation is angular velocity of the fifth Pauli multiplied by the R5. R5 is the uppercase letter 5. And we can find this considering the got previously, which is omega 5, the angular velocity of the fifth Pauli. We can find that the translational velocity of the point C is R5 divided by R lowercase 5 multiplied by the velocity V2, as we got it from the first got dependence of the angular velocity of this Pauli number 5 on the translational velocity of the load 2. So having the translational velocity of the center of the roller 5, we have here the instantaneous center of the velocities in the point of its location of connection with the support surface. And this is P point, and because this roller moves with no sliding, that is a point connected, this instantaneous center of velocities, and what is the angular velocity of omega 3 is equal to the translational velocity of the center of this roller divided by the radius of this roller. So we have radius R3 of the roller, we divide the translational velocity by the R3, and we have what is V3 translational velocity, the same as the velocity of the other rim of the fifth stepped Pauli. Then we have this as from here of translational velocity of the V3. After the substitute, we can find the dependence. That the angular velocity of the roller V3 equal to other radius of the stepped Pauli R5 divided by the internal radius of the stepped Pauli 5. R lowercase and R uppercase and divided by R3 is the radius of the roller through number 3 assigned as well. Okay, the angular velocity of the stepped Pauli 4, what is it? We defined everything by the translational velocity of the load, subject to find V2. Angular velocity of the Pauli 4 is equal to the translational velocity of the point B equal to the translational velocity of the center of the roller equal to because they connected by the thread and equal to the velocity of the point C translational, and we can find the angular velocity as the V3 divided by the internal radius assigned R lowercase 4 of the stepped Pauli number 4. After a definition by the considering here the translational velocity V3 as we got it here before, so and substitute, and we can find that the angular velocity of the stepped Pauli 4 wedged Pauli. This was a wedgeless. This is a wedged Pauli. Equals to the ratio R5, the other radius, R uppercase 5 divided by 2 R's lowercases internal radiuses of the Pauli 4 and the Pauli 5 multiplied by the velocity of the which we use as a by which we redefine the all elements of the motion of all elements mechanical system. It is the velocity of the subject to find of the load 2. And what is the velocity of the load 1? This is the same as the velocity of the point on the rim of the fourth Pauli. So we multiply the radius of the rim of the fourth Pauli, R uppercase 4 assigned multiplied by omega, this velocity of the rotation of this Pauli, the omega 4. And after the substitute of the omega 4 from here, we will have that the velocity of the load, which is load, this load with no mass of this load is the ratio in the numerator. We have the product R4 and the R5, the upper cases of the other radiuses of this two-stepped Paulis. And the denominator we have R lowercase 4 and the R lowercase 5 is a numerator. So this ratio multiplied by the velocity subject to find V2. So we redefine the elements of the motion of all elements by the translational velocity of subject to find of the second one load. We can as well summarize this all in the table 10, 11, 1. So this is a case K, the number of the element of mechanical system. First element, second, three, etc. This is the translational velocity of the elements. For the Pallas 4 and 5, we do not have translational velocities as they are with a fixed location of the axis of the rotation. And with angular velocities for the motion of the first and the second loads, they do not rotate. They do not rotate. So we do not have the angular velocities, and we have only for the Pallas and for the roller number 3. It moves and it rotates, and the Pallas rotates there only. Okay. Next, to find the kinetic energy magnitude, we have to define the characteristics of the inertia of the element of the mechanical system. Let's go consequently. Most inertia of the roller 3 and the Pallas for are equal to m3 for the roller 3, m3 multiplied by r3 squared divided by 2. This is for the moment of inertia relative to the center of the mass of the roller number 3, and I4 is the moment inertia of the stepped Pallas number 4, m4 mass of the Pallas number 4 multiplied by the squared radius of the rim, because it is assigned that the mass of the force Pallas distributed evenly by the rim of the force Pallas. The kinetic energy of the load first is 0, because the load is mass is 0, so massless load. Kinetic energy of the mass second is equals. So as of the second load is which velocity we have to find, equals to, we have in the mass 6 kilos equals to the mass multiplied by squared translational velocity divided by 2 of the second load. And this equals, because 6 divided by 2 is 3 of squared velocity of this load number 3. This velocity v2 subject to find. The kinetic energy of the homogeneous roller with the mass 2 kilos equals. So we have the roller, we have to define this energy by the velocity subject to find of the second load as well. So this is subject, we have to define all kinetic energies by the subject to find variable, as we have to find the velocity of the second load. So we did redefine the kinetic energy of the first load by the independence of, of the second load. We have this second here. The first load is 0. First load is of the 0 mass. This have to be 2 second load. 2 second load is 3 by, in the table, in the summarizing table, 10, 11, 2. We have the T2. T is kinetic energy of the second load measured with the mass. We have 3 by V2 squared. Yes, I'm sorry for this different one error. It have to be 2 here. The kinetic energy of the homogeneous roller, because this roller on the one hand rotates, and on the other hand moves translationally. I mean, the motion of the center of the velocity. The kinetic energy of its move in translational motion is equal to the product of the mass of the roller by the squared velocity of the roller divided by 2, plus the moment of inertia of the roller. This is cylinder or disk with a homogeneous distribution of the mass within the disk, multiplied by the angular velocity of this disk or of the roller number 3 squared divided by 2. Next, we use a redefinition of the translational velocity of the disk by the velocity of the load, because we have to define all energies by the velocity of the second load squared, as we have to find this finally, this velocity. So when we substitute that, and when we substitute instead of the moment of inertia, it definition by the as a standard formula we have for even distribution of the material within the homogeneous cylinder or disk, we will have m3 multiplied by r squared divided by 2. And 1 second, this goes from the formula of the kinetic energy of rotation, and multiply by the squared angular velocity of rotation. This omega 3, we got it here, we got it before, independence on the translational velocity of the second load. So omega 3 is equal r5 divided by this r3 and r5 lowercase multiplied by omega by the v2 velocity of the magnitude velocity of the second load subject to find squared. We don't forget that in kinetic energy, this is squared magnitude. So after the set of the data assigned, we can gradually define. We said the mass, the radius, this two comes from the formula. As well, we have the factors and the mass and the as well the radius is proportion, etc. So gradually we come to that the dependence of the kinetic energy of the roller total is 6 by v2 squared by the variation with the variable have to be assigned the velocity of the second load subject to find within the system. Kinetic energy of the step Pauli 4 with mass 3 kilos equals this Pauli step Pauli experiences only the rotation because its axis is in the fixed location, so it rotates only over the fixed axis. So we have the mass, and it is only the kinetic energy of its rotation equal to moment inertia of this Pauli 4, and we have the even distribution. This 2 comes from the formula of the kinetic energy. We have even distribution of the mass along the rim along the other rim of this step Pauli. This we got here this I4 is defined as mass of this Pauli multiplied by r squared for the distribution by the rim of the mass. That's like the ring about this. About it looks like the moment inertia of the rotating ring multiplied by the angular velocity v4 squared. But angular velocity omega 4 redefined by the translational velocity of the second load subject to find. This is when we set the radius is all and everything we have to set, the mass, etc. And we will have that the kinetic energy of the force Pauli rotating, not moving, but just rotating, not translationally movement, is 13.5 multiplied by the velocity of the second load, because we defined the limits of the motion of this rotating Pauli by the translational velocity of the second load. Okay. The kinetic energy of the step Pauli is 0 because the mass of step Pauli number 5 is 0 assigned. The total kinetic energy of the 5 assigned elements of the mechanical system. If we do the total of this all, we can summarize this in the table. The forced mass less load is with moved load with 0 kinetic energy. The Pauli number 5 is massless Pauli. We have 0. This is force Pauli. It only rotates, not moves. So this is kinetic energy of rotation. This is roller. It possesses the kinetic energy of rotation, the same as translation motion of the center of the mass. And the T2 is the kinetic energy of the motion of the second load. And together they are 22.5 multiplied by the squared velocity translational of the second load. Okay, we define the kinetic energy of all mechanical system by the velocity of the second load, which we have to find. So the kinetic energy of mechanical system changes under the work of the external force. We only have force which moves this whole system. This is assigned force 50 multiplied by in the brackets 3 plus 4 by SS as a coordinate of the motion along the inclined surface of the forced load, which is weightless load with mass equal to 0. The constant moment as well we have of the resistance of the fifth Pauli. It is assigned 0.3 Newton by meter acting on the Pauli 5. The work of the external forces we have only of 4 components. The first component, the work of this force assigned external force, which is defined by this definite one equation. Second is the work of the weight action on the lower 2, which has the mass and the moves along the inclined surface. As remember, 45 degrees inclined surface. And the work of the friction, because this second load is on the inclined surface, and this load as well caused the normal force to the surface. So this force, this load when moves experiences friction too, and the work of the resistance moment applied to the fifth Pauli. Translational moments on which external forces F, P2 is the weight of the second load, F, external force assigned to the force of the friction, the moment, and the time when the load 1 moves a distance. So it is assigned to find the velocity of the second load when the first load moves a definite distance. The distance was assigned 1 and 2 meters by the inclined surface, as I remember, inclined at 30 degrees. Let's define the element of the motion we did for the velocities, but what is for the displacements? Can we redefine the displacements of all the listed elements as the first element assigned the motion is for 1 and 2 meters for the specified time, for the specified state of the system to find the velocity of the second load. What is the path of the second load when the force goes for 1 and 2 meters? What is because these two works of the weight of the second load and the friction force acting on the second load applied on the direction of the motion along the inclined surface, as I remember, for 45 degrees. They depends on the distance of the motion of the second load as well. And what is the angle of rotation of the fifth Pauli under the action of the moment of the resistance M5? So we have to redefine all the displacements, translational displacement and angular displacements. So to find next the work of the external forces on the mechanical system, and these displacements all we have to redefine by the assigned displacement of the first load under action of the indicated force F on S, and the displacement have to be 1.2 meters. So the angle of rotation of the force Pauli will be under action will under the kinematic action of this displacement translational. The first load of each listed load we have to divide by the order radius R4 and equal to 4 meters. When we set the radius and we set the assigned displacement of the first load. The translational motion of the third element mechanical system, that is a roller which moves and rotates as well. So the translation motion is equals to phi 4 is the angle of the, we have 4 radians, what we previously multiplied by the radius of the internal radius R log his letter of the stippled polar number 4. When we set that all, or we just can use it from here for, or we just can do this proportion of the radiuses, and we can find it as 0.8 meter. This is when the load 1 moves for 1 and 2 meters, the roller 3 moves translationally for 0.8 meter. Besides, the angular motion of the fifth Pauli wedge less power is equal to the motion of the roller S3 as well. This roller does not cause any kind of the external work. Why? Because it moves in the horizontal direction. This moves on the horizontal surface. So the forces, external force acting on this definite one roller, are directed to upward as a force of direction of the surface and the normal direction, and the wedge force directed downward. So these two forces are perpendicular to the direction of the motion of this definite one roller. So we don't need to have the elements in the very details, like the element of the rotation of this, like the displacement, angular displacement of this roller, or translation only. We have to find that only as to find the angle of the rotation of the fifth Pauli, because this is under action of the external resistance moment, as these forces do not cause the work do not cause the change of the kinetic energy of the mechanical system, because these forces are perpendicular to the direction of the motion of definite one roller number 3. So we go just right to find the angle of rotation when the load assigned number first load moves for 1 and 2 meters. What will be the angle of rotation of fifth Pauli at the direction of the external resistance moment? This is equal to the motion of the roller, translational motion, that is the motion as the other surface. The roller moves the same as the point C moves here, translation literally. But angle rotation, if this roller moves together with the point A, so we can find that the angle will be equal to the ratio of the R4 divided, as initially this is the translational motion of the third roller divided by the other radius of the fifth Pauli. This we have order radius of fifth Pauli, the motion of the third roller, this translation motion S3. Here, the same as S3, the motion corresponding to the point C and divided by the outer radius, external radius of the fifth Pauli. So we will have that after the set of data of R4 uppercase, R5 uppercase, etc. We can, when we set S1 is the displacement of the first load at which we have to find the velocity of the second load. The angle of rotation of the fifth Pauli will be equal to 2 radian. And what will be the translational motion of the second load? This is the angle of the rotation of fifth Pauli multiplied by the internal radius of the fifth step Pauli. So if we have the angle of the rotation is Pauli and multiplied by the radius internal of this fifth Pauli, we will find the translational motion of second load when the first load gradually by the sequence of the drives move this second load. The first moves for 1 and 2 meters. What will be the motion of the second load at the definite one time? So we will have that proportion. The proportion got of the previously got for 5. We have the proportion definite one. We multiply this proportion onto R5 lowercase, and we can find that it is equal. We as well set here the displacement of the first load, weightless load, but the direction of this one external force. And we will have that the motion of the second load will be, after the mathematical transform, 0.4 meter. Somewhere we can have in the table 10.11.3. 10.11.3 contains the dependency displacement on which act the external forces. The force assigned to applied to the first one load, the force pi to the weight of the second load, exactly in the projection on the direction of the motion of second load, and the friction force of second load, and the moment of the resistance of the fifth Pauli on the assigned displacement. And this is the magnitudes, the equations, the magnitudes as well got previously. Okay, now we have to find the works of the external forces. The work of external forces we have on behalf of the assigned load. We have the work of this on the assigned load, as I don't remember, it's 50. Next, multiply the brackets. What is the brackets we have? This 3 plus 4 by S, etc. This is dependence of the external load applied to the first weightless load. Work of the external force, excuse me. This is external force. 50 multiplied by this one, what we have in the brackets, the 50 outside the brackets. And the work of the force of the weight of the second load, and the force of the friction of the motion second load, and the force of resistance of fifth Pauli. Okay, we'll go gradually. First is the force integral from 0 to S of the force by ds. Force in the direction of the motion of the first weightless load. So we can find this formula. the limits of the integration from 0 to at time moment equal to 0. The location is 0. The time moment, the definite time moment, we at the end of the integration, we have the displacement for S equal S1 and 1.2 meters ds. Yes. So this is the limits in the ds. After the disclosure of this integral and after the set of the data, what is S1 here, we can find that the work of the force acted on the force load by its displacement for 1 and 2 meters, 1 and 2 meters here, 1 and 2 squared. After disclosure, we have squared in the bracket, second sum, etc. In the first, we have the just displacement 1 and 2 meters. And it is equal to 324 Newton by meter. Newton by meter, that is joule. Joule, units of the work, units of the energy in the international system of units. Work of the weight of the second force, because the second force is on the inclined surface. Excuse me. First of all, let's put your attention, please, that all other works are with a minus sign. Why minus sign? Because all three forces, as the force of the weight of second load, the force of the friction of second load, and the force of the moment rotation, they are the frictions arise when the system begin moving. This is a force, it's acting, but this all forces, this all works are with a negative sign because they all are resist the motion of the mechanical system. Only the first force acts for the motion of mechanical system with the definite magnitude of the work 325 N by M, the force applied to the first weightless load. Force of the weight, the force of the friction. Let's consider, please, this system. So we have the second load. The first was weightless. The second is with a definite weight assigned. We have the force of the gravity, force of the weight of this load. The weight is the mass of the load multiplied by 9.91 is acceleration of the gravity. And it is the load is on inclined surface, and we have to find the projections, a vertical projection of the force and the horizontal projections. We have the angles here, the right angle triangles of 45 degrees. So in the first case, to find the not horizontal, but parallel to the plane of the motion of the second load, the projection of the wedge force, we have to multiply by sine or by the cosine of 45 degrees. It's not so much important because this both two angles are 45 degrees. If it's adjacent angle, so we have to multiply by the cosine. If we consider the other angle, we multiply by sine of 45 degrees. But anyway, the cosine and sine of 45 degrees is equal to square root of 2 divided by 2. Yes. And this was the horizontal component of the force. It caused the work of the wedge force resisted the motion of the whole mechanical system, and the first load, which is weightless, and just only additional external force working. And the second component, normal to the surface, N2, caused the friction as well, the subject for the resistance of the motion of the mechanical system. So to do that, so we multiply by sine alpha, we multiply by sine of the angle of the inclination, finding the work of the wedge, finding the component of the force wedge parallel to the parallel but opposite in direction to the motion of this second load, and we multiply by the cosine 45 degrees, the same magnitude, square root of 2 divided by 2. When we consider the normal force on the surface on behalf of the second load with the friction factor, this caused the friction force. So after the set all magnitudes here, as the mass, the acceleration of the gravity, the sine of 45 degrees, and the got previously the displacement second load, when the first one moves for 1.2 meters, the second moved for 0.4 meters. We got it previously, as we got it here, 0.4 meters here. And the same we can, after the all substitute, we found that it is minus 16.65 Newton by meter, the work of the wedge force resisting the motion of the mechanical system. And the work of the friction force as well, we substitute the friction factor multiplied by the mass of the force multiplied by the gravity acceleration multiplied by the, this is the wedge together, two factors, multiplied by the cosine of 45 degrees, the same as the sine. For 45 degrees, the magnitudes are sine and cosine the same, and multiplied by the same path of walking of the second load when the first goes for 1.2, the second goes for 0.4. And we can find that the work of the friction force is minus 1.66 Newton by meter. And the work of the moment of resistance action on the fifth pulley, minus this moment of resistance multiplied by the angle of the rotation fifth pulley when we got this angle of the rotation fifth pulley is is 2 radians, yeah. Yeah, 2 radians. When the translational motion of the first load is assigned 1.2 meter. So we multiply the assigned magnitude of the moment of resistance by the angle, and we can find that the work of the force moment of the resistance of the fifth pulley equal minus 0.8 Newton meter. We do this all summarized in the table. So this is the work of the external force assigned. This is the work of the force of the wedge against of the motion of the mechanical system of the second load. This is the force of the friction second load, as well resistant the motion. This is work of the resistance moment of the fifth pulley, this with the minuses, with the first one with the plus. And the resultant work of the external forces is equal to 304.89 Newton by meter. This is joule units of the energy or the work in the mechanics. The velocity we can find as if we equate the kinetic energy got previously, kinetic energy of all mechanical system independence on the velocity of the second load squared, 22.5 velocity of second load squared, and we have to find what is the velocity of the second load when the first load goes for 1 and 2 meter. When it goes for 1 and 2 meters, the work of the external forces will be equal 304.89 Newton by meter. And we just equate this to this kinetic energy from the state of rest of the mechanical system. So we have only the final kinetic energy. And after the equation of 304.99 to the 22.5 by V2 squared, we can find V2 squared. V2 squared is 3.04.89, what is it? 89, yeah, they have to be 89 under the root. And this equals to 3.68 meter per second velocity subject to find. So at the moment, time the load first moves at a distance 1 and 2 meters, the velocity of the load 2 is equal 3.68 meter per second. This result got by the use of the theorem of the kinetic energy change. Questions and comments. 10, 11.1 indicators including the law of energy conservation of a system which is not upon external forces action. The kinetic energy which characterizes the motion of a mechanical system and its element and depends on the translational and angular velocities and on the characteristics of inertia, the masses and moments of inertia of masses. And the potential energy characterizing the coordinates of elements of mechanical systems, location and conservative forces acting on this element, the work of which when moving along the closed path or during the rotation is equal to 0. Yeah, in a more general approach, the types of the energy we consider in mechanics is 2, the kinetic energy, which characterizes the motion of the mass of the elements which possess the mass or characteristic of inertia of rotation. So not only the mass, but as well the distribution of mass, which characterized the inertia in the rotation. And besides, we have to consider in the mechanics the potential energy which characterized not by the velocity of the mechanical system, but on the action of the forces and location of the conservative forces. Conservative means the forces which do not cause the work when we consider the rotational motion in particular, or the motion on the closed path. This energy is of the action of the conservative forces equal to zero potential energy. But actually we have two energies in the mechanics, 10, 11, 2. The kinetic energy of mechanical system equals to sum of kinetic energy values of all moving elements of system. Yes, it is. The energy of each moving element of mechanical system is either equal to the total of the kinetic energy of the translational rotational motions, taking into account the inertia of the body in translational rotational motions, or equal to the energy of rotational motion of an element of mechanical system relative the instantaneous center of velocity, taking into account the inertia of the body when rotating relative to the center of the velocity. Yes. In a more general approach, the kinetic energy in the plane motion or in the spatial motion that is in the space equal to total of the motion translationally of the center of the mass of the element of mechanical system or the total mechanical system, and the rotation of the mechanical system around the center of the mass. Or we can consider, instead of the center of the mass, the instantaneous center of the velocities. And in this case, we will only consider the rotational motion of the element mechanical system or mechanical body, or just a set of the material points like concentrated loads, etc. The rotational motion. But the characteristics of inertia of the rotation in the second one case will be other than in the first one. So in the second one case, we have to consider the inertia of the rotation, not relative to the center of the mass of mechanical system, but relative to the instantaneous center of the velocity. And this characteristic of inertia for the rotation corresponds not only to the own characteristic of rotation relative to the center of the mass, characteristic inertia of the rotation, but as well the transfer characteristic of the inertia of rotation, assuming as well the rotation of the center of the mass relative to the instantaneous center of the velocity. 10.11.3, the kinetic energy change theorem, considering zero influence of the work of internal forces acting between the elements of the mechanical system on the change of kinetic energy of the system, showing the equality of the kinetic energy change and the work of the force acting of the elements of the mechanical system. That is true if only not we are talking about the elastic bodies. For the rigid bodies, stiff bodies, solid bodies, we consider only the external forces. What if we have like the elasticity, the springs, etc., within inside the mechanical body or mechanical system connecting the discrete element of mechanical system, or just the material points, the concentrated loads, etc., connected by the elastic elements of the mechanical system? As well, we have to consider the internal forces too, having the kinetic energy change theorem consideration. Yes, we have to do for the elastic bodies. For the rigid bodies, absolutely rigid bodies, or the solid bodies, as we to say. So we do not have to consider the action of the internal forces when finding the change of kinetic energy of the mechanical system. 10.11.4. Determination of the motion indicators, the translational angular velocity of mechanical system, interconnected elements by the motion indicator of one of these elements. For example, velocity of the moving load doing work that causes the movement of the elements of mechanical system and changes their kinetic energies. Because one of the final goals in the issue is to redefine the elements of the motion of all mechanical system by the element of motion of just only one element, to do this, to do the systematization of the motion of mechanical system. So the relevant is to select the element of the motion which is or assigned. Which motion is assigned. For example, the velocity is assigned, or the displacement is assigned when we have to find the velocity. And we have to redefine elements of motion of all element mechanical system by this motion of this definite one element of mechanical system. This is methodic approach. Thank you.